In the second part of our discussion on chemical vapor deposition, we shall take some examples of some materials to grow those materials by CVD. We shall take the example of silicon, we shall take the example of gallium arsenide, we shall take the example of indium phosphide, because those are the important materials which we take as example. Now, you see that there are various CVD techniques. Apart from AP, LP, PE CVD, there may be halide process, there may be hydride process, there may be organometallic chemical vapor deposition process. As the name implies, the halide process means you start from the halide complex or compound of a material. Halide compound means silicon chloride, chloride is a halide. Okay. Hydride means some compound containing hydrogen, say arsine, ASH3 is the hydride, PH3 is the hydride, or organometallic chemical vapor deposition, that means chemical deposition from the organometallic sources. Organometallic sources means the source containing some organometallic compounds. Organometallic means it is a organic compound of some metal, say gallium, like this trimethyl gallium. Trimethyl gallium, that means gallium is a metal in group 3, this is group 3 of the periodic table, and trimethyl is the organic compound. So, trimethyl gallium is a organometallic. Similarly, trimethyl indium, that is also a organometallic of indium. Similarly, triethyl aluminum, it is also an organometallics of aluminum. So, it can be trimethyl, it can be triethyl, any organic organometallic source. So, that is a different chemistry. There are some personnel who work on organometallics. There are some advantage of organometallic sources. These are the basically known as the precursor, P-R-E-C-U-R-S-O-R, precursor. You have to start from a precursor. Your precursor can be halide, your precursor can be hydride, your precursor can be organometallic. Okay. So, these are the precursor to start with a reaction. Now, if you see the halide process, you will find that in halide process, say for gallium arsenide, for growth of gallium arsenide, AsCl3 is put in a bubbler through which hydrogen is passed. What is AsCl3? Arsenic chloride. So, it is a halide, okay? Halide of group 5, because arsenic is the group 5 of the periodic table. And you can ask me, sir, why AsCl3? What is the speciality of AsCl3? There is no speciality except that it is liquid, high purity liquid. Similarly, gallium is also a liquid at room temperature. You know that gallium is a liquid. The advantage of liquid is that you can purify it by successive distillation method. You can purify a liquid by the method of successive distillation, because in semiconductor the purity is very, very important. So, AsCl3 being a liquid is put in a bubbler through which hydrogen is passed. The resulting gas flows over the gallium source and then onto the substrate. What is the substrate? The substrate obviously will be gallium arsenide, because you would like to grow gallium arsenide. The reactor tube is heated in the source region to about 1000 degree centigrade. and in the deposition region to about 800 to 850 degrees centigrade. So, that means you see that from this discussion it is evident this is a two zone furnace. One zone is 1000 degree containing gallium, another zone where the substrate is kept, it is 800 to 850 degrees centigrade. So, that means you can think like this. This is 1000 degree centigrade, this is 850 degree centigrade. Here the substrate is kept, here in a boat molten gallium is there. Okay. So, what happens? AsCl3 plus hydrogen is passed to the reactor chamber. This is inside a reactor chamber. This is inside a reactor chamber. There is vent. That means the byproducts will leave the reactor chamber, and obviously there will be heating elements. This is heating elements you can control, so that in this region the temperature is 1000 degree and this region 850 degree centigrade. Now, we have talked about a bubbler. In a bubbler there is one inlet and there is one outlet, and you can change the temperature. Okay. You put AsCl3 in the bubbler, AsCl3, there is one inlet, there is one outlet. Depending on the temperature of the bubbler, this space will be filled with the vapor of AsCl3, because it is already a liquid and the vapor pressure is a function of the temperature, right. So, at a particular temperature, say 40 degree, 50 degree, 60 degree, whatever be the temperature, there will be sufficient vapor pressure on the surface of the AsCl3 inside the bubbler. So, when hydrogen will pass through the inlet, that hydrogen will carry not the liquid AsCl3, remember liquid cannot be carried, it will carry the vapor of AsCl3. It will carry the vapor of AsCl3. So, when I write this type of a thing, that means it is the hydrogen gas, high purity hydrogen gas and the vapor of AsCl3 coming out from the bubbler with the help of hydrogen. Okay. The reactor tube is heated in the source region to about 1000 degree centigrade and in the deposition region to about 800 degree centigrade. When the AsCl3 saturated hydrogen flows over the source region, the following reaction takes place. That means, this AsCl3 saturated H2 vapor, it will come to the source, means the gallium region. First it will come to the gallium region. So, what reaction will take place? This is the reaction that will take place. That means, see AsCl3 gas, G stands for gas, plus 3/2 H2, this is also gas, it becomes arsenic gas and 3 HCl gas. Okay. So, this is the reaction which takes place. First this reaction will take place. So, what will happen? HCl will be formed, HCl gas in the form of gas. Then the HCl formed in this reaction reacts with the source gallium to produce GaCl according to this reaction. Ga, what is this? This is L, liquid. So, gallium liquid plus HCl gas, you will get gallium chloride, it is a gas, plus H2, it is also gas. In the next phase we shall see that this GaCl and hydrogen will react with this arsenic to form gallium arsenide. You see the following reaction then takes place over the heated substrate, resulting in crystalline growth of gallium arsenide. So, here at 1000 degree centigrade, what happens? First AsCl3 reacts with hydrogen to form As plus HCl. I am not balancing the reaction. Okay, As plus HCl. Then this is the first step, step 1. Step 2, then gallium is a liquid, it reacts with this As, it reacts with this HCl, GaCl plus hydrogen will be evolved, this GaCl. Then the next reaction will take place in this region. Here the temperature is less compared to this. So, there will be condensation. There will be condensation because the temperature is less. You think of that bulk crystal growth where the molten gallium arsenide is kept in one boat and the seed is what? Pulled from the melt. So, what we find? We find that at the interface between the molten state and the seed, there will be a temperature difference where the crystallization takes place, the condensation will take place because of the temperature gradient. Here also there is a temperature gradient from 1000 degree to 850 degree centigrade. So, there will be crystallization of the gallium arsenide. So, here the reaction will be like this GaCl plus As plus hydrogen, you will get gallium arsenide plus HCl gas. So, what is the byproduct? What is the byproduct? Yes, HCl and H2. HCl and H2, these are the byproduct. And also the unreacted AsCl3, because there is no guarantee that yes, it will completely, it will be decomposed. So, that is the byproduct. Now, you think of the process step 7, process step 6 and 7. In process step 6 and 7, what we see? The desorption of the byproducts and diffusion onto the main gas stream. So, these are the byproduct. This HCl is the byproduct, H2 is the byproduct, unreacted AsCl3 is the byproduct. So, these are the byproduct which you find, and this will be diffused onto the main gas stream and it will go out through the vent line. I shall show you one chamber of CVD in my laboratory. So, all those things it will be very easier for you to feel. Where is the gas line, where is the inlet, where is the outlet, where is the pump is put, where is the susceptor, how the susceptor is put inside the reactor chamber, how the substrate is kept on the susceptor. So, and how you can, more important thing is how you can control the various kinds of gases, because until now we have not discussed about any controlling parameter. Suppose you need some 10 cubic centimeter of gas, 5 liter of hydrogen you need, okay, per hour or per minute. So, those controlling parameters, how it can be controlled, because there is a control setup, it is totally by the computer control or manually you can also undertake the growth. Normally, I am talking about this hydrogen. Normally, this hydrogen, you know what is the flow rate of this hydrogen? The flow rate of this hydrogen is typically 2 SLPM. What is SLPM? Standard liter per minute. Per minute 2 liter of hydrogen you have to flow through the bubbler. Then only it will be possible for the hydrogen to carry this ASCl3 to the reaction place. Otherwise, there will be no flow. You have to make the flow on. So, this is the 2 SLPM. In some cases, I shall show you that it can be 5-6 liter per minute. So, that means huge quantity of gas is required per minute. So, if there is a growth of say 60 minute, so per minute if there is 2 liter, for 60 minute how many liters? 120 liters per hour. So, you have to sustain the flow of hydrogen through that rate to support the growth. So, those can be controlled. How you can ensure that it must be 2 SLPM, not 3 or not 4 or not 1. There is mass flow controller. You can set the mass flow controller and the mass flow controller will control in that manner. I shall show you that setup. So, this is the halide type of growth, and for p type doping you see that zinc is used, that we have discussed many times, and for n type doping sulfur or selenium in the form of H2S or HAC, H2AC, hydrogen selenide, hydrogen sulfide, those are used for n type doping. One important aspect of this chloride based VP that it produces very pure layers, since the liquid source can be made very pure by distillation. That is the important aspect of this thing. But what is the problem with the chloride or halide? It is very corrosive. Chlorine is very corrosive. So, pressure care must be taken. So, that is also there. In all the processes you will find some advantages and disadvantages, it is always there. Now, if you take the example of hydride process, you see that in hydride process gaseous ASH3 or PH3 are used as the sources for group 5 elements. That means, you see that all the time we find it is the game with the group 5 elements. Chloride, in case of chloride we have used ASCl3, arsenic chloride. Here it is the arsenic hydride, that means arsine, or hydrides of phosphorus, that means phosphine. So, all the time we are using the group 5 elements either in the halide form or in the chlorhydride form. The hydrides decompose in the high temperature zone of the furnace according to this. That means, arsine is decomposed into arsenic and hydrogen. Then this HCl reacts with metallic group 3 source to produce the chloride, say GaCl. That means, you have to inject HCl gas, remember, you have to inject HCl gas. So, in zone 1 where there will be 1000 degree centigrade, this HCl reacts with gallium to form gallium chloride, and the other reactions are same like the halide process. Halide process means you see that this type of thing. Okay. So, this reaction gallium plus HCl, here ACl3 is converted into HCl. So, there is a reaction between gallium and HCl. In the hydride process you find that there is no HCl. So, we have to make input of HCl. That HCl gas will react with gallium to form GaCl, and this arsenic comes from ASH3, decomposition of ASH3, not Cl3. In halide it is Cl3, but in hydride this arsenic comes from the decomposition of H3, it decomposes into AS plus hydrogen. Okay. The rest of the reactions are the same reactions. Yes, this is a CVD reactor of horizontal reactor. Why it is horizontal? Because the gas flow is in the parallel to the surface, Here you see that there are 4 wafers which are placed on the susceptor. The susceptor is graphite, and this is various kinds of gases which are sent to the reactor chamber. This is for the silicon, not gallium arsenide, because here we have used SiCl4, that we shall discuss also. So, if we now discuss about the CVD of silicon, you see that there are 4 sources. One is silicon tetrachloride, silicon tetrachloride. Silicon tetrachloride. Okay. It is SiCl4. This is the most important precursor which is used for the silicon CVD. Industrially this is used, but the temperature is quite high, 1200 degree centigrade. It is almost 1200 degree centigrade temperature is required, because you have to decompose this SiCl4. You have to decompose this SiCl4. There are other sources, because as I mentioned that there are 4 sources. One is silicon tetrachloride, number 2 is dichlorosilane, that means SiH2Cl2. Number 3 is trichlorosilane, SiHCl3, and number 4 is silane. So, these are the 4 important sources. One is silicon tetrachloride, another is dichlorosilane, number 3 is trichlorosilane, and so on. SiCl4 is the silicon tetrachloride. Okay. Now, what we see? We see that if we start from silane SiH4, you see that in this case one H is replaced by Cl. H is replaced by Cl, or if we start from SiCl4, Cl is replaced by H. Here you see that in this trichlorosilane, one chlorine is replaced by one hydrogen. If this is the case, then 50 degree temperature can be reduced to decompose that material. For one substitution of chlorine by hydrogen, 50 degree centigrade temperature can be reduced to decompose. That means, here it is the temperature is 1200 degree centigrade, here the temperature will be 1150 degree centigrade. Similarly, here 1100 degree centigrade. In this case 1000 degree centigrade, okay? Because you see that here all the 4 chlorine atoms have been substituted by hydrogen atoms. For every substitution there will be a reduction of 50 degree centigrade. So, lower temperature growth is possible, but purity, gas handling criteria, those are there. So, that is why only the silicon tetrachloride is the most effective precursor for silicon growth. Okay, so, we see that there are 4 sources, one is silicon tetrachloride and dichlorosilane, trichlorosilane and silane. Those can be used for the silicon CVD. Here you see that silicon tetrachloride is sent to the horizontal reactor by the application of hydrogen, that means hydrogen as a carrier gas, right. Sometimes we have seen that in some cases HCl is required. So, there must be some inlet of HCl, okay. Then there must be some inlet of dopant. Dopant means if you can grow p type or n type silicon, then you have to use the dopant. So, different kinds of gas lines are there. You can use these gas lines for sending different gases to the reactor chamber. It may be typographical mistake. One will be dopant plus H2, another will be another dopant plus H2. It can be H2, it can be N2 also, N2 you can use, but problem is as we have discussed is the purity. Handling nitrogen is very easier than hydrogen, but problem is with the purity. We need 9N or 10N purity, and you cannot purify nitrogen to that level. Hydrogen is very easy to purify because of the diffusion of hydrogen through the palladium cell at 300 degree centigrade. Okay. So, at the input in a palladium cell you send hydrogen, impure hydrogen, and if you heat the palladium cell at 300 degree centigrade, at the output you will get 9N, 10N pure hydrogen. So, very easy to make. Even in the laboratory you can use a palladium cell through which the hydrogen can be passed. If you come to my room, I shall show you how a palladium cell looks like. It is very easy fabrication. Okay, now no, you cannot. First thing is that you know that it is very costly. Second thing is that purification not very easy like hydrogen, and availability. Where is the helium availability? Hydrogen and nitrogen is widely available. Now, if you see the reaction, it is SiCl4 silicon tetrachloride, it is gas. It reacts with hydrogen gas to form Si solid plus 4HCl gas. This is the overall reaction, because your input was silicon tetrachloride, and that silicon tetrachloride with hydrogen reacts with hydrogen in at that temperature at 1200 degree centigrade. It is 1200 degree centigrade. Silicon solid plus HCl. So, what is the byproduct? The byproduct is obviously HCl is the byproduct. Another is the unreacted this part. Unreacted this part, that is also very important, that you have to sweep that gas through the reactor towards the vent. And another thing is that this SiCl4 gas, when reacts with silicon solid, SiCl2 gas is formed. So, what we see from this reaction? We see from this reaction that this solid silicon which you have formed, it can react with silicon tetrachloride to form SiCl2 gas. That means, if the quantity of SiCl4 is large, what will happen? There will be reversible reaction, and so instead of forming the film can be etched. Solid silicon means what? Solid silicon means the film. So, the top of the film can react with silicon tetrachloride to form SiCl2. That means, there will be etching, there will be removal of the silicon film from the substrate.
This SiCl4 is byproduct.
Which one? Which one?
Second one, which is reacted with silicon.
Yes, but we don't want it. You cannot avoid it, but we want it, because we have started to grow silicon. Why we shall lose silicon? Because this reaction, through this reaction we shall lose silicon.
Sir, SiCl2 is stable?
SiCl2 is a gas. So, basically it will go out from the reactor.
Silicon is a tetravalent.
Yeah. No, I am not making the balance reaction. Only thing is that SiCl2 will be formed as a gas and it will go out from the vent. Okay. So, what people do? You have to quantify this SiCl4. In this view graph, you will see that this is the quantity of SiCl4. So, as the quantity of SiCl4 increases, the growth rate increases. For a particular value, it attains the peak. Then, as you increase the SiCl4, the growth rate decreases. Okay? Then, if you further increase the SiCl4, then there will be etching, because you see this is the 0 line. Above the 0 line it will be growth, below the 0 line it will be etching, that will be etching. So, you have to choose very small amount of SiCl4, that means the growth must be kept in this region, only in this region. In this region you will find that the growth rate is not so high like this portion, but you need not to worry about the etching of your material, and also it is linear. So, you can quantify the growth rate from the quantity of SiCl4. Okay. Very small amount of SiCl4 you have to take. So, that is not applicable for silicon epitaxial growth. This is applicable for all materials. When you use a particular material in the vapor phase, either in chloride or in hydride form, you have to check whether there will be any reversible reaction which will degrade the performance of your growth process, whether there will be etching, whether there will be removal of your material from the surface. If there is substantial removal from the material, then that will not be cost effective, and this high purity material you have to lose, that will go as a waste product, you cannot use those things. So, that means the costing will be very, very high, because all the material whatever we use, even if we use HCl or H2 gas or N2 gas or SiCl4 gas, it is very, very costly because of its purity level. It is not industrial grade or normal laboratory grade reagent. Okay. So, you have to very careful about the quantity or the amount of SiCl4 for silicon epitaxial growth. Now, what are the dopants? For silicon growth? Gaseous diboron, it is p type, and arsine phosphine n type. Okay. So, you can use two types of dopants. One is the gaseous diboron B2H6 for p type and ASH3PH3 n type. But here one point you must remember that this is diluted. What is dilution and how the dilution is made and why dilution? When I talk about this diboron or arsine or phosphine, I have used the term dilute this material. Which material? This B2H6 or ASH3 or PH3. Why? Why dilution is required? Dilution is required because of two reasons. One reason is that no, not for toxic, it is no, it is to control, because we have seen in our bulk crystal growth that very minute amount of this material is required. Can you remember one example where I have used that for 50 kg of silicon, only some 3 to 5 milligram of dopant was used. So, how will control? For controlling you have to dilute. How you will dilute? You have to dilute with hydrogen, mix hydrogen more and more, so that it will be diluted, and there is a calculation procedure. You can use a computer simulation program that what amount of hydrogen is required for the dilution of what amount of ASH3 or PH3. So, that you can calculate using some simulation program or using some chemical calculation. You can arrive at how much dilution is required. So, dilution means you can send the exact amount, one point. Second point is that you can control also. Very small amount is required. So, control becomes very difficult unless you make it very dilute. Suppose without dilution, say 0.0002 liter per minute is required without dilution. 0.0002 controlling is very difficult to make, even if you have a very good mass flow controller, because of the practical limitation of the mass flow controller. But if you can dilute it by 10 to the power 4, then it becomes 2 LPM. If it becomes 2 LPM, then controlling of 2 LPM is very easier to make by the mass flow controller. So, one thing is the control, another thing is the amount, very minute amount is required. So, theoretically you can have without dilution also, but how you will control it? So, that is why hydrogen is mixed with these dopant gaseous sources for its control and minute quantity interaction in the reactor chamber. Okay. So, physics people you can leave. Now, one thing we shall discuss about this substrate, the effect of substrate, that is very important. You see that effect of substrate is very important to make, that for epitaxy you have to use lattice matching substrate. Lattice matching substrate means the lattice constant of the substrate will be same as the lattice constant of the film to be grown on the substrate. Lattice constant of substrate will be same as the lattice constant of the grown layer. Grown layer means, what is grown layer? Grown layer means the thin film or the epitaxial layer you are growing basically. Now, if there is a mismatch between the lattice constants, then what will happen? Dislocation. But there is another important aspect, that is why I am again introducing this thing, that you have to use some temperature, higher temperature during growth. In almost all the CVD techniques you will find that it is 600, 800, 1000 degrees centigrade temperature is involved. If the substrate and the grown layer are of different material, suppose your substrate is silicon and you are growing gallium arsenide, then what is the problem? Apart from the lattice mismatch, the thermal expansion coefficient of the silicon is different from the thermal expansion coefficient of gallium arsenide. So, there will be more stress, there will be more stress. So, not only that it is a normal lattice mismatch, that is applicable for normal room temperature value. If your material and the substrate is of the same constant, then it is okay. You are using silicon on silicon, you are using gallium arsenide on gallium arsenide, it is okay. Whatever be the temperature, the thermal expansion coefficient will be the same for both the cases. So, there will be compensation, right. But if you use different type of substrate, then the thermal expansion coefficient is different, and because of the thermal expansion coefficient, there will be thermal stress also, that will give you the dislocation. Okay. Then sometimes we find that, suppose you want to grow gallium arsenide on silicon, then very small, very thin gallium arsenide layer is can be grown without any defect, very small. Why? Because there will be a stress, but if the layer is very small, then there will be no stress. That is known as the critical thickness. For all the material, you will have a critical thickness. Above the critical thickness, there will be dislocation. Up to the critical thickness, there will be no dislocation. But if your critical thickness is say 6 angstrom, 8 angstrom, can you grow with that precision? No, you cannot grow with that precision. So, that is the problem. If you can grow, then it is possible to grow gallium arsenide on silicon, but you have to keep the critical thickness, the thickness of the grown layer below the critical thickness. Below the critical thickness, it is possible to grow any kind of layer, but the critical thickness itself is very small. It is the order of 8 angstrom, 6 angstrom, 10 angstrom, which normally you cannot grow even if you have a very good epitaxial machine. Because if the growth rate is say 8 angstrom per second, then how you will grow 6 angstrom layer or 8 angstrom layer? It will have less than 1 second, but less than 1 second control is very difficult to make. So, always you will find that you cannot grow below critical thickness, it is always above critical thickness. If it is always above critical thickness, then you will find that there will be dislocation. Okay. So, we can summarize in this manner that substrate say substrate is A, layer is B. Thickness of layer B must be less than equal to critical thickness of B on A. Remember that B on A, that means critical thickness will also change. Critical thickness will be different for different pair of materials. For B on A, it can be x angstrom. For B on C, it can be y angstrom. For B on D, it can be z angstrom. So, it depends on a pair of material. Remember that the critical thickness is not a fixed dimension or fixed thickness, it depends on a pair of material. Okay. So, thickness of layer B must be less than equals to the critical thickness of B on A, which is x angstrom, right. Now, this is very important, and if this is possible that the thickness of the layer B is less than equal to critical thickness of B on A, then this is known as the pseudomorphic layer. That layer is known as the pseudomorphic layer. Remember that for pseudomorphic layer, it will be free from any kind of stress or strain. Okay. Now, one important aspect of this thing, you see that we have discussed that there are three CVD techniques. One is the halide, another is the hydride, and third one is the organometallic chemical vapor deposition. So, we shall conclude today's discussion with that organometallic chemical vapor deposition, some parts of the organometallic chemical vapor deposition. In organometallic cases, it is known as the MOCVD, metal organic chemical vapor deposition, or organometallic chemical vapor deposition, same thing, or metal organic vapor phase, it is not coming, metal organic vapor phase epitaxy. Okay. So, it can be MOCVD, it can be OMCVD, it can be MOVP, it can be OMVP, the same thing. Same thing. The main aspect of this growth is that we are using a CVD technique, and in all the CVD technique the process 1 to 7 is fixed. So, here also process 1 to 7 we shall apply. Only thing is that we shall not use any halide sources or hydride sources, rather we shall use metal organic sources. For metal organic sources or organometallic, the same thing, we shall use the trimethyl sources or triethyl sources, not of group 5, not of arsine or phosphine, but of the group 3, that means gallium or indium or aluminum, of gallium or indium or aluminum. Okay. If we talk about the 3,5 semiconductor growth, if you grow other type of material, then you have to choose some efficient precursor for that material, organometallic efficient precursor. Okay. Say silicon, if you have silicon organometallic precursor, then you can grow silicon also. So, you must have a organometallic precursor, that is the precondition. Material having organometallic precursor can be grown using emissivity. Material having no organometallic precursor, you cannot grow by emissivity technique. You have to use different kinds of techniques. But this is very fruitful and very efficient and very popular technique for 3,5 semiconductor growth. 3,5 semiconductor means gallium arsenide, indium phosphide, indium gallium arsenide, etc., indium gallium phosphide. That means any combination of group 3 and group 5 elements of the periodic table. In group 3, what are the materials? Gallium, indium, aluminum. In group 5, what are the elements? Arsenic, phosphorus, antimony. So, those things you can use because very good organometallic precursors are available. In emissivity, the reaction temperature is less compared to the halide or hydride growth. That is one advantage of emissivity. Advantage of emissivity is that it has a temperature lower than the halide or hydride. Okay, it is a temperature lower than the halide or the hydride, right? Lower temperature than lower growth temperature than halide or hydrides. That is very important thing. Number 2, excellent doping profile. Excellent hetero junctions. So, those are the advantages of emissivity, right, and low dimensional structures. What is low dimensional structures? What is low dimensional structures? Low dimensional structures means not thickness, it is quantum well, quantum dot, quantum wire, nanostructures, those are known as the low dimensional. Low dimensional means it is less than 3 dimension. So, we have discussed that thing, that splitting of the energy bands. Yes, I have given you the example of this room, that if suddenly the roof falls on you, so what will happen? What you will do? That you will not be able to stand. So, we have to swim on the floor of this room. Basically, we have to lie down on the floor. So, that means you can move through the x and y direction, but on the z direction you will not be able to move through. Similarly, if these two walls, side walls come closer, then what will happen? We will not be able to move on those two sides, only on the z direction you can move. That means you can jump, but you cannot move on x and y direction. So, that is the quantum wear, that is known as the quantum wear. That means your movement is restricted on two directions. On x and y direction your movement is restricted, only you can move on the z direction. Similarly, when the roof comes closer to the floor, you have no option but to lie down on the floor. So, there also you can move on the x and y direction, that means on the floor you can move, but on the z direction you cannot move. So, if you can move on the x y direction, that means that is known as the quantum well. Okay? 2 dimension and you are free to move, but your movement is restricted in one direction, that is the z direction you cannot move. So, likewise, if all the walls and the roofs are come closer, very close to the floor. Yes, then you are unable to move in any of the directions basically. So, that is known as the quantum dot or the nanoparticle. And under those conditions the energy level splits because of the Schrodinger wave equation and Pauli's exclusion principle. If you can solve those things under boundary conditions, you will find that there will be the splitting of the energy levels, and because of the splitting of the energy levels many fundamental new properties are obtained or are found for those nanostructures or nano dimension. That is known as the low dimension. That is known as the low dimension. Okay. So, where the dimension is not 3 dimensional, it is either 2 or 1 or 0, right. So, we shall discuss in our next class how these low dimensional structures are made using CVD and also MBE. Okay. Thank you.